Thank you everybody for visiting our talk. My name is Minje Kim from Indiana University, and this work was done by Zhen, my former student, and my collaborators at ETRI in Korea. Today we are going to talk about the psychoacoustic models that are applied to neural audio coding so that we can improve the performance of the coding system. But in doing so, we actually came up with the new loss function to train our neural network system for audio coding. This work was actually already published in IEEE Signal Processing Letters in November 2020. So please try not to find this paper in the proceedings because it's not going to be there. Let me first introduce what audio coding is about using neural network. There have been two different kinds of neural audio coding systems in the literature, which are all gaining a lot of attention these days. The branch one is something using parametric coding, some parametric representation of speech, and using some decoders that are basically generating the speech signal out of the code. So it works pretty well mostly for speech, and it's typically based on WaveNet decoder or something synthesis-based ones. And they work pretty well, actually really well when it comes to the, especially in the low bit rates. So it's very nice in the regard, although it relies on the complexity of the decoder pretty much. It's with high time and spatial complexity, although there have been some recent follow-up work that's using simpler decoders like LPCnet. The other branch is using autoencoders, which is basically, taking the input waveform and then recovering the input waveform as much as possible. So it's usually with a smaller model size, lightweight, because it's using CNNs and it's with the lower latency as well. But the performance is not as good as the branch one cases, especially in the low bit rate. In this work, we are going to use a autoencoder-based approaches because we care about the audio quality, the exact reconstruction, and the bitrate is relatively higher. We argue that this is first work applied psychoacoustics to neural audio coding, especially the simultaneous masking, so that we can improve the audio quality and the coding efficiency and the model efficiency as well. So let me introduce our basic audio coding architecture, which is basically some kind of a stacked CNN layers. And it's a straightforward autoencoder. First, it consists of an encoder, obviously, that takes the time domain signal or frame and then converts it into the latent representation, which is going to be our code in the floating point domain, of course. And in doing so, it's going to go through some nonlinear layers. So basically, the transformation is nonlinear. It's going to find some latent space where the coding gain is maximized. But at the same time, you can try to reduce the data rate or sample rate by introducing some stride in the CNN layers. So that's our encoder. And our codec is with the quantization layers in the middle, actually, which actually works as a part of a model inference, and it can be trainable as well. What's nice about this quantization in the middle architecture is that it can, of course, reduce the bit depth of each dimension. But in addition to that, we can, for instance, compute the entropy of the quantized codes during the training. So if the entropy is too large, for instance, we can penalize it by using some loss function and so on and so forth, so that we can control the entropy and bitrate accordingly. So that's pretty nice in that regard. And finally, we are going to use some decoder, which is going to recover the input signal from the quantized code, and in the way it may want to reduce the quantization artifact, and its goal is to recover the original low samples as exactly as possible. So it's a pretty straightforward autoencoder architecture proposed by Kankanahali, and it's an autoencoder system machine learning model, so we need a loss function. And here we're gonna, for instance, use some sum of scared error, which is very typical, and we have some recovered time domain sample and the ground truth sample as well. We square the difference and then sum up the error across the samples and data examples as well. But this is actually not reflecting the human auditory system or the perceptual quality of the audio. So we could try to be clever here and try to do something better than this, which is loss function computed in the male spectrum domain, so that we can pay more attention to the low frequency area. Because if you convert your time domain audio into this time frequency domain and then apply the male scaling, for instance, then after the conversion, we have more resolution in the lower frequency and less resolution in the high frequency. So if we compute the loss in this male scaled domain Y sub L, where L is the index of the frequencies, then it's kind of automatically computing focusing more on the low frequency area than the high frequency area. And it's reflecting our auditory system, and it's pretty nice. Again, these are all objective metrics, and they are not necessarily reflecting the perceptual quality of the audio as much as we need. So, but at the same time, we also know that psychoacoustics, for instance, played a big role in MPEG audio coding technology for the past decades. For instance, if there is two quiet tones that are not audible, the ones that are below the threshold in quiet, for instance, then maybe we don't have to care too much about it, try to encode it and decode it properly. What's more interesting in simultaneous masking is that if there's a big masker tone like this one, the loud one, then another tones around this masker tone could be masked by the masking threshold generated by this masker tone. So it means that from the codex perspective, it has no reason to spend too many bits to represent this guy, because for instance, if it indeed uses smaller number of bits, and it can actually introduce some quantization noise by this amount, but it might be still fine because after the quantization noise added to this reconstruction, it's still below the masking threshold, so the error is not audible. So we incorporated this concept into our neural coding system by first implementing our own PAM1 model based on the painter's paper. So, as usual, we compute the absolute hearing threshold and all the toner and noise maskers and their corresponding masking threshold, and we aggregated everything together to come up with this global masking threshold, the red line, and it's the masking threshold that's corresponding to the input spectrum, the blue signal. And we implemented this PAM in TensorFlow because our goal is to somehow convert this idea into a loss function. So we implemented this and we open sourced this. Once that part is done, what we're going to do is we're going to compute our psychoacoustic loss function, which is called the priority weighting. And it's, again, another model that's parameterized by the power density function, P, and the masking threshold that we just computed using our own implementation, M. And we're going to examine some subbands and then see if the subband is important for the model or not based on this mask. For instance, if there's a peak like this, the tone which is exceeding the mask, then it means that this tone is audible to the human ears according to the psychosis masking threshold that we computed. So we're gonna pay more attention to this guy during our model training because it's an important one. But at the same time, there could be some other tone which is below the masking threshold. It means that this tone may not have to be exactly reconstructed by the neural network because it's not going to be audible. So what that means is that when we train this neural network-based coding system, we're going to use this weight that's over frequency f, and we're going to compute the third loss term in the frequency domain And in each subband, frequency subband, we are giving different weights. If the weight is large, it means that this frequency is important, audible, and the network has to pay a lot of attention. But at the same time, if the weight is small, then it means that the network doesn't pay attention, allowing some error. So the model can kind of create some room for the from the inaudible area and then pay more attention to the audible area so that it sounds much better eventually, or maybe you can save some bits along the way. And when it comes to this weight, actually it's nothing but the simple ratio between the power spectrum density and the mask. And then if the power spectrum density is larger than the mask, then the weight is larger because it means that it's an important area. So that one actually works pretty fine, but we also found that it cannot really completely remove the noise that's exceeding the mask. The first method we introduced was kind of indirect. So we came up with another final loss term called noise modulation, which is inspired by the MP3's iterative beta location algorithm. So when you think of the MP3's beta location algorithm, it first computes this concept called noise to mask ratio. And it's basically computing this yellow area. If there's a yellow area, it means that the noise is louder than the mask. And MP3 is going to assign more bits to the yellow areas iteratively so that it can kind of suppress the noise accordingly. So as for this high noise to mask ratio areas, we represent this as a loss function as well. We first compute this NMR concept first, and then if it's larger than 1, then it means that the value function is going to be activated and contribute to the loss. If it's smaller than 1, it means that the noise is actually smaller than the mask. Then in that case, the value function isn't going to be activated, and it means that that subband actually doesn't contribute to this loss. So by using this value function, we can identify which subbands are creating these yellow areas that are, exceeding the masking threshold. And once that's done, we compute this maximization function that's selecting the worst case, the highest noise that's far exceeding the mask, and then address that. So it's an iterative algorithm. At a given epoch, the optimization is going to address the worst case and then try to suppress that area. And in the next epoch, if the model visits the same example, then it's going to work on the other yellow area and so on and so forth, which is kind of similar to the beta location algorithm in MP3. And this algorithm can work along with the other loss functions that we have seen so far, and maybe can fix the mistakes that the other loss functions are making. And once it's done, we can actually finally suppress the noise in this way, which is actually the output of our system. So this loss function is working. So let's first see if the first psychoacoustic loss function priority weighting is working. It works. If I compare model C and B, where model B is the one that's not using the perceptual loss at all, and model C is the one that's using the priority weighting in addition to the other sum of scares or Merrill scaling loss functions. As you can see here, model B is actually using higher bitrate, and its model complexity is twice larger than the priority weighting method. But the performances are kind of similar to each other. It means that the priority weighting can reduce the bitrate and the model complexity while maintaining the audio quality, which is great. If I compare model C and D, where D is the one that's with noise modulation in addition to the other loss functions, and we can see that it's actually better than model C that's only using priority weighting in the same bitrate and same complexity. If I compare model D with the smaller bitrate and smaller architecture to the larger bitrate and the larger architecture, we can see that model D can scale up to the larger bitrate and then compete with MP3 finally. So it means that our model can scale up to the higher bitrates nicely. So to summarize, we proposed the two perceptually motivated loss functions that are improving the coding efficiency, model efficiency, and the audio quality, and then compete with MP3. If you're curious about our work, please visit our website where you can find the source codes and the audio examples as well. Thank you for your attention.